Okay, welcome back. This is C++, and we're on page 350 in Chapter 8. And in Chapter 8, we're now beginning to look at built-in arrays. Chapter 7, we had used array template and created array objects. Now we're looking at built-in arrays. Now, a built-in array is a fixed-size data structure used in a declaration as type, array name, angle bracket, array size, angle bracket, semicolon, where we have a required type and an array size. So in our built-in array, for a declaration, our kind of generic form is type, array name, angle brackets, and then the array size, angle bracket, and semicolon. Now, we must have the type, that's required, and it's required that we have the array size. Remember that built-in arrays are a data structure that is a fixed size. They neither grow nor shrink during program execution. Now, the compiler reserves the appropriate amount of memory then, given the array size and knowing the data type, as each type has its own requirement for number of memory bytes for storage capacity. The array size must be an integer constant greater than 0. And to tell the compiler to reserve 12 elements for a built-in array of integers, we might have something like int, array name is C, angle bracket 12. And that would be an array by the name of C. It is a built-in array of 12 integers. We're using subscript notation with the angle brackets. And that's subscript 0 through 11. Remember, we're always off by 1. Also, the angle bracket operator for representation of the subscript within our built-in array. The angle bracket operator does not bound check. That is, doesn't check for the memory bounds beyond the array itself location. So bounds checking for array template of objects or built-in arrays, there is no capacity that provides for that. You have to be responsible to make sure that you do not address beyond the capacity of the array. You can also initialize the elements of a built-in array with something like int n 5, and then with the braces we're initializing and we're going to initialize the elements of this array. They're integers 50, 20, 30, 10, and 40. So we have 5 elements of integer type stored within this built-in array. Always specify a built-in array's size. This enables the compiler to generate an error message if there are more initializers in the list than array elements. So if we had maybe an extra element in our initialization list, the compiler would be able to indicate an error message for us, which is always better than having a runtime error. Passing built-in arrays to functions. The value of a built-in array's name is implicitly convertible to the address of the built-in array's first element. So if we have array name, it is implicitly convertible to the address of array name at its starting point at subscript 0. So array name takes us to the memory location of array name sub 0, and it always will do that. So this is an address of array name sub 0, and array name is meaning the same thing. So implicitly, array name is an address. For built-in arrays, this means that the called can modify all elements of a past built-in array in the caller environment, unless the function precedes the corresponding built-in array parameter with CONST, indicating constant, to indicate that the elements of the array should not be modified. So in passing built-in arrays to function parameters, we have to understand that you're actually passing the address. So we are referencing and referring to the array in the caller environment. So items could be modified. Applying constant CONST type qualifier to a built-in array parameter in a function definition to prevent the original built-in array from being modified in the function body is an example of the principle of least privilege. Functions should not be given the capacity to modify a built-in array unless it is absolutely necessary. Declaring built-in array parameters in function headers, page 351. Declaring built-in array parameters in the function header. So we have int some elements for our function name. We're going to send as a constant our integer values array, and we're going to send as a constant the size t data type numbers of elements. So a function header, some elements, it's going to return an integer. We're passing a constant integer array by the name of values. We're sending it as a constant, so we are going to have a reference to the original array in the caller environment, but we will not be able to modify any of the elements within the array. And we're sending the constant number of elements in the array values, the size of array values, as a size t data type. This first part parameter indicates that the first argument should be a one-dimensional built-in array of ints, and that it should not modify the caller environment. Part 2, the second parameter that's sent, indicates that the built-in size will not be modified within the function. Built-in arrays, unlike array template objects, chapter 7, array template objects. Built-in arrays, unlike array template objects, do not know their own size. So a function that receives a built-in array must receive both the built-in array's name, and here we see part 1, the array's name, and the array's size. So as we're passing built-in arrays to functions, we need to pass the array's name and the array size. Built-in arrays do not know their own size. In section 7.7, we showed how to sort an array template object with the C++ standard library function sort. Well, it's nice to know function sort can be used with built-in arrays also. For example, to sort a built-in array, n, we can call the sort function with the begin of array n and the end of array n. And this will sort the contents of the built-in array by the name of n. Built-in arrays have several limitations. On page 351, they cannot be compared using relational and equality operators. You must use a loop to compare two built-in arrays element by element. Built-in arrays cannot be assigned to one another. An array name is effectively a pointer that is a constant. They do not know their own size. A function that possesses a built-in array receives both the built-in array's name and its size as arguments. And built-in arrays do not provide automatic bounds checking, so you must ensure that with the array access expressions used, that the subscripts are always within your array bounds. Page 352, 8.5.7. In contemporary C++ code, you should use the more robust array or vector class objects that we studied in chapter 7 to represent lists and tables of values. However, there are cases which built-in arrays must be used, such as processing command line arguments. C++ inherited built-in arrays from legacy code C. 8.6. Using constant with pointers, CONST. Recall that CONST enables you to inform the compiler that the value of a particular variable should not be modified. There's a rule: always give a function enough access to the data in its parameter to accomplish its task, but no more. This enforces the principle of least privilege. Built-in arrays are always passed by reference and could easily be changed in the called environment. If a value does not or should not change in the body of the function to which it's passed, then the parameter should be declared CONST. For example, int sum, oh, that'd be lowercase. Int sum. Sum is the name of our function. We're sending a constant int values, name of our array, our parameter name for an array that's being passed to it. We're sending values as a constant integer array, and we're sending as a constant the size and number of elements. Now, passed built-in arrays will not be modified. The passed built-in array that's passed to this array pointing to an integer will be passed as a constant. So the passed built-in array will not be modified in this function. And size t as the data type for number of elements will not be modified. It's a constant. So we're sending a built-in array to value as a array pointing, storing integer values, but it's a constant reference, so we will not be modifying the caller environment's values, elements within the built-in array. And passed to this function, we have a constant size t data type with the number of elements, and the number of elements will be a constant value and then not modified within this function. An attempt to modify a constant value is a compilation error, so it's good to design your code using a constant integer array as a constant array a parameter and a constant size for that array as a parameter. The compiler will trap the error for you and use the rule of least privilege. On page 353, there are 4 ways to pass a pointer to a function. A non-constant pointer to a non-constant data type. A non-constant pointer to a constant data. A constant pointer to non-constant data, and a constant pointer to constant data. On page 353, we examine each. Section 8.6.1, non-constant pointer to non-constant data. This is the highest access granted to a function. So if we're passing a non-constant pointer and a non-constant data, then those items can be changed in the caller environment. The data can be modified through the dereferencing pointer, and the pointer can be modified to point to other data. Section 8.6.2, a non-constant pointer to constant data. A pointer that can be modified to point to any data of appropriate type, but the data to which it points cannot be modified through that pointer. Our declaration would look like const int star count ptr. Now this declaration is read from right to left. Count pointer is a pointer to an integer that is constant. Count ptr is a pointer to an integer constant. So count pointer can be reassigned to point to a new address, but the data cannot be modified. So the data to which this pointer points cannot be modified through that pointer. So let's look at figure 810. Starts on page 353. And dissect the code. Okay, figure 810. A compilation error message produced when attempting to compile a function that receives a non-constant pointer to constant data, and then tries to use the dereference pointer to modify the constant integer data. Attempting to modify data through a non-constant pointer to constant data. Our function prototype expects non-constant pointer to a constant integer. So we have a function that's not going to return anything. F is its name. It is a pointer to a constant integer, read from right to left. We're going to have a pointer. Remember, in the prototype, you don't have to have its name. We're going to have a pointer to constant integer data. Main. Constant variable cannot be modified through X pointer. So here's our function void f int constant star X pointer. So X pointer is the name of a pointer to a constant integer. Here we're trying to make sure I have all the code. Okay, I got a problem with the code itself. Take care of that here in just a second. Chapter 8. Okay, missed a couple of lines of code. Okay, we're attempting to modify data through a non-constant pointer to constant data. Our prototype is okay. In main, we have an int variable y initialized to 0. And function f is passed the address of y. So f will attempt an illegal modification. We're passing the address of y to a pointer. Remember, pointers store addresses. So we're passing the address of y to the pointer. So X pointer is accepting the address of y. This is a non-constant pointer to a constant integer. So when I dereference the address to which X pointer points, I'm looking to modify or change the value at the address to which X pointer points. So I'm trying to reassign the value to which X pointer points. My attempt is to reassign 100 to the constant integer that X pointer points to. Let's see what happens. And I have an error message. X pointer you cannot assign to a variable that is constant. So we have an error and our project failed to successfully compile. And that's what we expected as we're testing a non-constant pointer to constant data. So we were unable to reassign data to a constant int through a non-constant pointer. So revisiting the code, a compilation error message produced when attempting to compile a function that receives a non-constant pointer. The pointer is not a constant to constant data, but it's pointing to a constant int value. So the int values that X pointer points to cannot be reassigned in this function. And then tries to use the dereferencing pointer to modify the constant integer data. So remember, the asterisk is our dereferencing pointer. The asterisk X pointer, that's the value to which X pointer points. We're trying to reassign it to a different value. Remember that we read in the function header from right to left. X pointer is, well, it's not constant, it doesn't say constant. The X pointer is a non-constant pointer to an integer constant, a constant integer. And again, we were expecting compilation errors. X pointer cannot assign a variable that is a constant. The next of our four is constant pointer to a non-constant data. A constant pointer to non-constant data always points to the same memory location. Our constant pointer always points to the same memory location. It cannot be reassigned within the function. And the data at that location can be modified through the pointer. So let's look at figure 8.11. All right, attempting to modify a constant pointer to non-constant data. In main, we have an integer variable x initialized to 3 and an integer variable y initialized to 4. PTR is a constant pointer to an integer that can be modified through PTR, but PTR always points to the same memory location as a constant. Constant pointer must be initialized before it can be used, so we're initializing PTR to the address of x. And the address of x is pointing to the integer variable 3. So PTR is initialized to a starting address, which will remain constant. read from right to left. PTR, its address will remain constant, and it's pointing to an integer value. I changed this just a little bit from the textbook to experiment. Cout, we're going to output the value of x, which is initialized to 3, and then we're going to dereference the pointer and ask for the value pointed to by pointer to be equal to 7. So we're reassigning the value pointed to by pointer. Now, pointer is a constant, but the integer value that it's pointing to is not. This is non-constant data with a constant pointer. So the address of pointer cannot be changed, but the integer value that pointer points to can be reassigned. So that should be allowed. We'll see when we check our output. And then we're going to output the dereferenced value that pointer points to, which should be the new value, 7. And I just commented out line 19, which is where we're going to test to see if an error does occur. Let's see what happens so far. We have 3 and 7 as output. So we are printing the output of x, which is 3, and then we're reassigning the value that PTR points to 7, and PTR points to the address of x, so x is reassigned 7, and then we output the value that PTR points to, which is 7. So 3 and 7 are output. Marking this up a bit, we initialize x to 3 and y to 4 as local variables in main, and then we call, well, then we assign the pointer as a constant pointer. So I just on my notes try to re-emphasize that. I use color and pointer as a constant, so its memory address cannot change. And it's going to point to an integer. Sure enough, it does by pointing to the memory address x. We output x's value, which is 3, and then the value pointed to by PTR is reassigned 7. And sure enough, we have a constant pointer pointing to an integer, so we're going to reassign this to 7. I'm not changing the pointer constant address. I'm changing the value that the constant pointer address points to. And then I'm going to output the value pointed to by PTR, which is now 7. And sure enough, maybe you can see that, maybe you can't. It's 3, 7, and then press any key. Next on page 355, we're looking at, again, from page 353, we have the 4 ways to pass a pointer to a function. And looking at each individually. On page 355, we're going to inspect passing a constant pointer to constant data. Now, the minimum access privilege is granted by a constant pointer to constant data, which means that the pointer will always point to the same memory address location and cannot be modified within the function that's passed to, and the data that at that location cannot be modified by the pointer. So this is the least privilege passed to a function, giving minimum access. The constant pointer will always point to the same memory location and cannot be reassigned within the method function, and constant data uh, at that location cannot be modified by the pointer. So let's look at figure 12. This is figure 12. We're attempting to modify a constant pointer to constant data. We have in main a local variable x initialized to 5 and a local variable y, both of type integer. PTR is a constant pointer to constant integer data. PTR always points to the same location. The integer at that location cannot be modified as constant data. So in the declaration we have, we're referencing PTR for the first time. It has to be initialized to a memory address as a constant pointer. So we have from right to left, the memory address of X is assigned to pointer, which is a constant pointer. Its memory address will not change during the execution of this body of code, and it's pointing to an integer, which is a constant. So the declaration read from right to left. PTR is a constant pointer to an integer constant. We're going to output the value pointed to by PTR. This is allowable. The value pointed to by the dereference pointer PTR, the asterisk PTR, is a dereference pointer. It always points to the value. It will return the value pointed to by PTR. We expect that to be 5. Pointer is storing the memory address of X, and it's pointing to an integer 5. We use the dereference variable. The value pointed to by PTR is going to be assigned 5. Now we would expect this to be an error because the value pointed to by PTR is a constant data value. So our data should not be changing either. And then we have PTR, well, that's our constant pointer. It should always point to the address of X. We're attempting, as a constant, we're attempting to reassign PTR a new address location, and we expect that to be an error as well. And sure enough, we have errors in line 16. Yep, that's where we expected our first error to take place, when we were trying to reassign constant data from 5 to 7. And in line 17, PTR you cannot assign to a variable that is constant. And PTR was declared as a constant pointer. Its address should always point to address of X. We're trying to reassign it to the address of Y. So this is a successful compilation error trap or catch. We were misusing some of the features and capabilities, and we're demonstrating that your compiler can trap those errors for you, and the reasons why we want to use certain types of pass pointers and data by constants to functions. So data will not be changed, and memory address will not be changed during the execution of your function. Okay, next we want to look at size of on page 356. The size of operator on page 356. The compile time unary operator of size of determines the size in bytes of a built-in array, or actually any other data type, variable, or constant during program execution. The size of operator, when applied to a built-in array, returns the total number of bytes in the built-in arrays. Remember, the total number of bytes as a value of its size. So size of operator is a unary operator, and it determines the size in bytes of a built-in array or any other data type, variable, or constant during program compilation. So let's look at figure 813 on page 356. Figure 813. Size of operator when used on a built-in array's name returns the number of bytes in that built-in array. So we have an array with 20 elements of type double. Since double is 8 bytes of memory, 20 elements, each storing a double that requires 8 bytes, means that the size of numbers as a built-in array with 20 elements of type double would require 160 bytes on our system. And remember, size of is system dependent. The number of bytes in the array is, and we're calling the size of operator on numbers, which is our array of doubles. And then the number of bytes returned by get size is. The function is get size numbers. We're passing numbers as a built-in array reference, address location to PTR. PTR is a pointer to a double. PTR stores the memory address, so return the size of PTR. Well, PTR is a memory address. It stores a memory address. So what's its capacity? How much memory is it requiring? Let's run the program and see. The number of bytes in the array is 160. That's what we expected. It's a numbers array with 20 elements of type double. And on our system, a double requires 8 bytes. So if we have 20 elements, each requiring 8 bytes, that'd be 160 bytes. The number of bytes returned by the getSize function is 4. GetSize, we pass the memory address location of numbers to the pointer PTR, which stores a memory address location. So what is the size of the memory stored at PTR? Well, I guess it's requiring 4 bytes. On page 357, determining the sizes of fundamental types, a built-in array, and a pointer. Figure 8.14 uses size of to calculate the number of bytes used to store many of the standard data types. So we'll get a understanding of our data types and the capacity used in memory to store those data types. The output was produced using default settings on a Mac. Remember that size of is a platform dependent operator. So when we run on a Windows machine, long is 4 bytes and long is 8 bytes. So let's see what happens on our system, figure 8-14. All right, we're using the size of operator on many of our standard data types to check their storage capacity. So we have a character, a short, an int, a long, a float, a double, a long double, an int array with 20 elements. 20 elements storing integers, so we need to know the integer capacity, the size of the integer, and then there'll be 20 of them, so 20 times the size of an integer. And we have a pointer to the array, and the variable pointer is pointing to an array. Pointer, though, stores a memory address, so we'll see what happens there. So let's run the program. The size of a character is 1 byte. The size of a short is 2 bytes. The size of an integer is 4 bytes. The size of a long is 4 on our system, and we're using a Windows system. The size of a long is 8. The size of a float is 4. The size of double is 8. The size of long double is 8. The size of array. Well, our array was declared to be 20 elements of type int. And type int is 4. So 4 times 20 would be 80 bytes. So the size of our array is 80 bytes. And the size of our pointer, remember your pointer is storing the address of the array. And the address of the array is array sub 0. And array sub 0 is storing an integer of the capacity 4. So that looks good. Remember that these demonstration files are all data student shared files, so you can run and execute your project to test and double check any of the information shared today. And as always, return to D2L. The lesson plan is chapter 8 for any homework, projects, tests, and due dates, and any additional details. Thank you very much.